So there's different ways in which variables can be related to one another. So far, we've been working with a single variable, one variable at a time, trying to figure out what the mean is, what the standard deviation is, and all that good stuff. Now what we want to do is figure out how two variables relate to one another, right? So we have different types of relationships, and those relationships are or they correspond to functions that you may have explored in the past, like linear functions or quadratic functions, cubic functions, quartic, exponential, natural log. If you're having flashbacks to college algebra or trig, that's okay. If you're having nightmarish flashbacks, don't worry about that, because we don't do that much of the algebra, college algebra stuff in here that it should be striking fear into your very soul. We do a little bit. We just we call back to some of the things that we talked about in those classes. Right? So, and like the names of things and what they look like. Not so much in terms of, like, I'm never going to ask you to factor anything. Let's just put it that way. Right. So, so yeah, if that makes you feel a little bit better, hopefully. I mean, that's the plan anyway. And in fact, as you probably discovered so far, it's pretty tech heavy in this class. Aside from the obvious thing of like you're learning through a computer, put that aside. I'm talking about like how are we evaluating statistics? Well, any class or any area of math in which the numbers are ugly, technology plays a vital role, right? Because it's just a matter of efficiency. Right? If you want to draw conclusions at a rapid rate, I mean, just think about the virus, for example. They say, oh, it's crazy. It's a miracle that we came up with the vaccine in such a short period of time. And it's like, well, compared to what? Compared to like 100 years ago? Compared to last year? I don't know. But if they're comparing it to the last time there was a pandemic, then, well, yeah, well, we better. Technology is advanced. The ability to conduct research clinical trials rapidly has improved greatly. And so it better be the case that we can do stuff like that more efficiently. I'm not saying that Desmos is the answer to those really pressing questions, but you know, it doesn't hurt when you start thinking along those lines. All right, so scatter plot is when we actually just looked at the scatter plot when we talked about normal probability plot. It's when you plot two variables against each other, right? And it creates an ordered pair. That ordered pair gets plotted as a point, right? And those points form either a pattern or they don't. If they don't form a pattern, we say that there is no correlation between the variables. If they do form a pattern, then it's probably going to be one of these patterns. And if it's not, then it's probably a more advanced type of function that's beyond the purview of this class, but you may still be interested in it, in which case we can talk, but it would not be the focus of the material that we're covering in this class. Right? So the way we determine whether variables are related, we take a look at the scatter plot, and we also determine what's known as a correlation coefficient. Oops, that's the wrong one. All right. So we want to talk about, specifically when we're talking about a linear relationship, we want to talk about whether or not there's a trend to the data and whether or not there are any points that deviate meaningfully from those data points, from the overall trend of the data. We call those striking deviations from the pattern, right? Any striking deviations could be considered an outlier, right? And an outlier, in its most basic sense, is a term that defines itself because, you know, it lies outside of the overall trend of the data, right? So when you look at a data set and you see, you know, I'll just do a rough sketch here. You got point, goose, you know. Pretty safe bet that this is going to be an outlier. This point over here. All right. So it doesn't take much in order to make a determination, or at least initial claim, that a point lying off the beaten path would most likely be an outlier. All right. In many ways, that's really all there is to it, because once you identify an outlier, the next step in the process is to try to figure out what to do with that outlier. Do we get rid of it, as in it shouldn't be there? Or do we focus on it, as in, ooh, I didn't see that coming? You know, like those, let's just put it this way. Like when you get the vaccine and they make you sit in a room for 15 to 30 minutes, they're trying to make sure you're not one of those outliers. You know, like those allergic reactions. Yeah, well, if you're going to have an allergic reaction, it's going to happen in the first 10 to 15 minutes or so. Like, oh, how nice. So the next 10 to 15 minutes will be the most stressful of my life. Got it. All right, great. Thanks. That's really heartening. But they're trying to make sure that you're not one of those outliers, because it happens, but it doesn't happen often enough that it would be a deal breaker for the vaccine. So it's something, okay, we didn't see that coming. We'll keep an eye on it, but we can't just dismiss it. So it's like you come up with a vaccine, and it turns out that in 0.1% of the population, a person's head is going to explode, like literally explode. I'm trying to be like hyperbolic here, so I don't make it too real. Like their head is literally going to explode. So do you say, well, it's only 0.1%? Like, that's hardly anyone. You know, well, 0.1% of what? What's the size of the population? That could be a lot of people. You know, you don't just dismiss it. You report it and you say, not likely, but keep an eye on this. Right? This is a possibility. Right? As opposed to maybe an error in data collection. You know, like you're surveying a population, and you know, like maybe elementary school students, and one student is age 5 and the other student is age 9. And when you were putting it in a spreadsheet, you forgot to hit enter after the 5. So you accidentally typed in 59. All right. So that's an outlier. But you can't just say, oh, yeah, there's a 59-year-old student there. No, you would say that was an error, right? That one would go, or a correction would be made, right? So in most cases, when it comes to outliers, it's just something you keep an eye on. But if you want to make a real analysis of the overall data set, you would generally disregard the outlier in the computation of correlation coefficients and also trend lines. All right, so that's what we're going to focus on now. You can see these nasty, but look at that formula. R equals nightmare. All right, and then you can see below that linear regression. All these notes: slope equals A equals nightmare, y-intercept equals B equals nightmare, and then some graph and calculator stuff. All interesting, I suppose. If you have a graph and calculator, we're not going to do any of that. What we will need to know is the R-squared values, the coefficient of determination. That's really important when it comes to determining the strength of the relationship between variables. So a lot of this stuff is either related to how you would determine correlation coefficients and coefficient of determination by hand, which we're not going to do. I used to make my my stat students do that. Only because that's how I learned it. And I was like, oh, yeah, well, we might as well. And then I was like, even I don't like doing this. So I tossed it. And I also have the idea that, like, well, you can't really appreciate a formula and how it works in a calculator unless you tried it at least once by hand. And you know what I came to understand over the years? I can appreciate a formula just fine without ever using it by hand. And so this is one of those. Look at that beast. Oof. So what you need to get from this is that we're going to compute R values and R squared values, R squared being the more important. The closer the R squared value is to 1, the closer the relationship is to perfection. All right. The closer it is to 0, the closer it is to the opposite of perfection. Yeah, the closer it is to no significant relationship between variables. All right. That's it. Without knowing what this R squared value is, it's like, okay, well, you're not really telling us anything, dude. I recognize that. I'm going to in 2 seconds, 3 seconds. So there's a little blurb here about making predictions and stuff, but it doesn't really mean anything until we start working on an example. So let's look at example 1. Ornithologists, scientists who study birds, tag sparrowhawks in 13 different colonies to study their population. They gather data for the percent of new sparrowhawks in each colony and the percent of those that have returned from migration. All right, so we're going to use the regression function to find what's called the least squares regression line, also known as the line of best fit. All right, this is the line that best fits the data. All right, so I got to zoom into right, so I apologize. So LSRL, least squares regression line, line of best fit. All right, so we need data, which we have. We're going to put that in a table. The first set of data, which would be your, what we call the explanatory variable or the input variable, that goes in for x1. All right. The second set of data goes in for y1. All right. So we type all that stuff in. Now this one, I do have a calculator up there on Blackboard. I kind of flashed through that really quickly earlier. I don't actually think that you need any particular special calculator for this because the built-in functions on Desmos work just fine. I'll show you real quick. But not too quick. Just the right amount of quick. All right. So we have all these values popped in there. I need my calculator to figure out the line that best fits the data. All right. So all you have to do in order for the calculator to do that is to type in the model of the function that you want Desmos to use when developing an equation that best fits this data, right? So we want a linear equation, but the form of the linear equation that we're going to use is the form y equals a plus bx. All right, so it's in this, it got the same structure as y equals mx plus b. If you're thinking about algebra, y equals mx plus b, slope and y-intercept, it's the same idea, except I moved some things around. Not me personally, statistics moved some things around. They prefer it this way because the a value represents the fixed quantity. That's your start. That's where your function starts. And then your change based off of that start comes afterwards. And that has to do with your slope. All right, there's a rationale behind it. All right, that's the model that we use. Desmos understands it slightly differently. So in Desmos, first off, the tables have the subscripts of 1 automatically built in, so we got to make use of that. So we have to say y1. Instead of equals, we're going to use a tilde symbol. A plus b x1. All right. Tilde, that tilde represents, I'm just going to clean that up. Actually, it just looks awful. A little bit better. That tilde represents regression. That's what Desmos understands as regressing to. All right. So the equation, the variable y1 is regressing to the form a plus b x sub 1. All right. There's never really a comfortable explanation for that one that doesn't really get into more advanced levels of statistics. So I just tend to leave it at that. It's just like, that's how Desmos speaks. And it's like, oh, okay, I kind of wish there was something better, but it is what it is. Right. So we just kind of live with it, unfortunately. So, but how do you type it in? Well, you type in the y followed by a 1. I'm still working on how the hell Desmos knows that I'm just by typing y followed by a 1 that I want a subscript of 1, but it just knows. Then you go into ABC. So you go into your QWERTY pad, and you could see 2 steps right. I'm sorry, to the left of the enter button is a little tilde. So grab that, and then type in A. Go back into your numerical pad, plus, and go back into the QWERTY pad, B, X, and you'll see it doesn't do it yet because I need that subscript of 1 in order for it to be complete. All right. So this is the regression equation. It doesn't seem like it did anything, because I'm looking at a blank graph. I got this printout here, which is nice, I guess. It's not really telling me anything more than I kind of already knew. So, oh, okay, well, at least we can write our answer down, because right below that, you see we have an A and a B, right? So what they're telling us, I'm going to resize this, get it out the way a little bit. They're telling us that our answer is y. So we go back to the correct notation, because we don't want to speak Desmos, we want to speak statistics. Y equals 31.934 minus 0.304x. All right, so that's the equation. Oh, I meant to use the lasso tool there. So that's the equation of the line that best fits the data, which is great. I still don't see a scatter plot, and I still don't see a line on my graph. It's like, well, did I do anything right? Well, it has to do with the domain. I'm going from -10 to 10 here, but if you look at the data points for my x values, they go as high as like 81. For the y1 values, they go as high as like 20. So looks like we're going to do a little zooming here. When you zoom out a little bit, you see there's a whole world of points here. And you can see here that you have a scatter plot corresponding with each ordered pair. So each one of these pairs of values corresponds with a point on the graph.
Professor?
Yeah.
Is it y equals a minus b or a plus b?
It's supposed to be a plus bx, but since the b value is negative, it becomes a minus.
Oh, okay, thanks.
So we have a data set that's showing a downward trend. It's loosely grouped, but we can get a line to go through a good amount of the points, just not a whole heck of a lot of them. right? So we have the best line to show the overall trend, but I don't think anybody'd look at this and say it's a good fit for the data set, right? Because just based off of the fact that it's missing a lot of the points, right? But we can do stuff with this. We can do some math with this, and that's the important thing. Because in B and C, it says determine the percent return if the percent new is 25. Well, percent return is the X value. The percent new is the Y value. So it's really saying determine X if Y is equal to 25. What that's telling us to do is set the equation equal to 25 and solve. But I stand by what I said before. I don't really need you to do any algebra. Right? So I'm going to show you a different way to handle that. One thing that I don't like about Desmos, well, there's a lot of things I don't like about it. But again, it's free. I can't emphasize that enough. There's some things that I wish would work better. One thing is this is an equation in appearance only. Like I can't do anything with this equation. I can't solve it in Desmos or anything like that. What I have to do is retype it in order to make it work. So what I do is I turn this off by tapping on that little graph icon to the left of it. You see it turns off the graph and it turns off the function itself. What I then do is I rewrite in Desmos, so rewrite it in function notation. So f of x equals 31.934 minus 0.304x. All right. The good thing, so I just told you something bad about Desmos, something I didn't like. Let me tell you something good. If you type in f of x equals, I don't actually have to type in those values because Desmos actually knows that a is the point of the 31 point blah, blah, blah. If you type in the a, it remembers that. It's stored in now. It also remembers that the b is the negative 0.304. So what I could actually do is in Desmos, just type in f of x equals a plus bx. Now, you might look at that and say, well, that did nothing. And I'm inclined to agree. You look at it and say, well, all it did was it put the same graph that was there before. Like I could turn that off. I can hit on that little icon there, turn it off, turn it on. Same as this one, turn it off, turn it on. It's the same graph, right? Back to square one, you might say. But I say, this is something I could actually work with now. I could do math on this. Because if you take a look here, when you turn this graph on, all you see is a black line, right? But if I turn this red line on, you can see those little gray points on the y-axis and the x-axis. So it'll already tell you what the x and y intercepts are if you just tap on those points. So it's already giving you more than the other graph would. But another thing it'll do is it'll allow you to evaluate this function, and it'll also allow you to find intersections between this graph and another graph, right? So if I know that y is means equals, right? So if I know y is 25, I know that fact. I could put that in as another equation and find the intersection between those 2 points and never have to solve. Because if you think back to algebra class, whenever you were given 2 equations with 2 variables, it was a system of equations and you had to solve. Here you have a system of equations you don't have to solve. Desmos will do it for you, right? So that y equals 25, that percent new equals 25. You put that in as a new graph, the intersection. Let me get a squiggly bracket here. 22.808, comma 25. Well, I already knew the y value would be 25. That's what I put in, right? So what I get here is the x value. They said find the x value. That tells me that x equals 22.808, which means that that's what the percent return is going to be. Right? So you actually get a lot more done with Desmos than you might have gotten done with an algebraic approach, with a different kind of graphing calculator. So it's something to keep in mind. Anyway. Now, if you don't like this technique, the other option would be what I said before, and that is take your linear regression equation, that y equals 31.934 minus 0.304x, replace the y with a 25 and solve for x. Some people prefer that, but I encourage you to at least try it with Desmos. Yeah, because the next question, determine the percent new, so the y value when x is 90. That's even easier with Desmos because you're just evaluating your function when x is 90. You're finding f of 90. And the good thing about Desmos is it understands function notation. So another good thing about Desmos. So I could just type in f of 90 and it'll spit out the correct answer, right? This gives us the y value when x is 90. All right, so that's about 4.572. And that's the percent new, because that's what they're asking for here. For quality build. All right, so yeah, again, it's an acquired taste, this Desmos stuff. I mean, some people, absolutely despise it, but even if we were using a TI calculator, you would. If you don't like Desmos, I don't think you'd be liking the TI calculator too much more anyway, right? Because there's an acquired taste here, but once you get the hang of it, it starts to make a little bit of sense. The TI calculator, people take years trying to learn that thing, and it never plays out the way they would hope anyway. All right. So overshot the Mac. So the last thing is the outliers and influential point. It's a new data set, but it's really asking about the same stuff. And the determination of whether or not there are any outliers or influential points, again, it's just a visual thing. So you just take a look and say, well, are there any striking deviations in the overall pattern of the data? So what I would do here is unfortunately, you do all this work and you say, oh, well, this was great work, good hard work. Delete, 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 delete. Now, it was wonderful, but it served its purpose. Now it's done. All right. So new data set. 1, 2, 3, 5, 9, and 11. 3, 5, 7, 10, 16, and 20. All right, so this is what my scatter plot looks like. So they're asking us to determine, so this is much more straightforward. The last one asked us to do a bunch of different things, but I didn't want you to, let's just put it this way. I didn't want to end class on a low note where people are like, what the hell is going on? I wanted you to look at a problem and say, oh, okay, wait a minute, maybe this isn't that bad. All right, and this is hopefully going to be that. All right, first thing you look at or notice, hopefully, is that there doesn't appear to be any striking deviations from the overall trend of the data. All right, so no striking deviations from overall trend. So then we would say, therefore, no outliers or influential points. The only way you'd have either of those is if you saw a point that was out of whack. You know, let's say, for example, instead of that last point being 11:20, it was like 11:2, you know, something like that. Everything else is on the same straight line, and then you got that one point that's out of whack there. But that's not the case. It seems like everything kind of falls on the same straight line. Once you've identified that there are no points that are out of whack, then you go right into the process of determining the linear correlation coefficient, which is the R value, and then the regression equation, which is the LSRL. Right, same thing we figured out above. Fortunately, it's the same process we figured out, or that we used above. Y1 tilde A plus B X1. All right, it says construct a scatter plot. So if I'm doing this for a test, this is what I'm doing. There's your scatter plot right there. Paste that bad boy right in. Save it for posterity. And then we get the regression equation, which again, we use the notation of y equals ax plus b, so 1.676, I'm sorry, a plus bx plus 1.643x. That's our regression equation. And they said to find the R value. R is 0.9987. You could say 0.999 if you want. Right? Now, they asked specifically for the linear correlation coefficient here, which is R. They could have said the linear coefficient of determination, which would have been R squared. Just got to know which is which. And that's all in your notes. Again, everything's an open notes assessment, so you have access to all this stuff. All right, so, you know, in a lot of ways, it's just a matter of having good notes and being able to recognize under what circumstances to use what process. But if you know linear correlation coefficient means R, then you got that part taken care of. In most cases, when people struggle on an assessment in this class, it has to do with the interpretation rather than the computation part of it, because computation tends to work itself out, right? But that's all this question's asking us to do, because once you've made a determination that there are no striking deviations from the overall pattern of the data, then you just go after it and you figure out your R and your Y equals, right? But the previous question, the data points were already kind of like haphazardly grouped. So like what pattern was there to deviate from, you know? So that's something to keep in mind. You know, you got to be thinking like, if there is no pattern, then how can you deviate from a pattern that isn't there? You know, so you wouldn't necessarily always be looking for those outliers. Right? So let me stop that video.